Alrighty, let's go ahead and work out these problems. So our first one here is we want to write a balanced chemical equation for the decomposition of ammonium nitrate into nitrogen, oxygen, and hydrogen gas. So what does that equation look like? State? Say again? No. Solid. It's an ionic compound, right? So it's either aqueous or it's solid. And decomposition reaction doesn't really require anything to be wet. So I'm decomposition into N2, O2, H2 gas. We okay with the equation? Or not? Oh, okay. I mean, are you okay with the, besides the not balanced part? Is it okay so far? So the nitrogens are balanced. Are we okay with that? The oxygens are not, and neither are the hydrogens. But we've got an odd even problem. So if I double, change colors here. If I double this to a 2, then I can put a 2 here, and now my nitrogens are balanced. And then I've got 8 hydrogens, so I can put a 4 right here. And I've got 6 oxygens, so I can put a 3 right here. Are you good with that? Okay, we've got 25 grams of ammonium nitrate. So 25 grams NH4 NO3, 3, and 1 mole NH4 NO3. Somebody have the mass? $80.0434 grams ammonium nitrate. And then I've got moles of ammonium nitrate. And I got moles of H2. And I have a 4 right there and a 2 right there. And then 1 mole. H2 is 2.0159 grams H2. And then we got some number of grams of hydrogen gas. Okay, does anybody have that mass? Something like 25 divided by 20? I don't know. Somebody got a mass? 1.3? That sounds good to me. 1.3 grams. Okay. Does anybody know what this reaction is? Besides a decomposition reaction? Like what happens here? It's definitely also a redox reaction. Do we all see that? All the products have what oxidation number? 0. And on the reactant side, they all have an oxidation number because they're in a compound, so they must be charged in some way. Think about what you have here for a second. I've got a solid, and then what happens to the solid? What was that?
Sublimation?
No. Sublimation, you have the same substance. It just turns from a solid into a gas. So I've got a solid, and what happens to this solid? Everything turns into a gas, right? So what do you think would happen if you had a solid, and then that solid just immediately turned into a gas? I'm not really sure what that has to do with it, but
Would it be a combustion?
no, it's not combustion. Why not? There's no O2 on the reactant side. right? Do you guys know what this is?
Oklahoma City.
It's the federal building at Oklahoma City. So that Timothy McVeigh thing. What was it that he did?
Ammonium nitrate, fuel oil.
He took ammonium nitrate, which is what this is here, and he allowed the ammonium nitrate to decompose. Well, what's this reaction we had? It's a decomposition. So I have a solid, and the solid turns into a gas. Tell me something about gases and solids and their size relationship. Bigger, right? What's the density of a gas-ish? It's about 1,000 to 10,000 times less than that of a solid. So now I've got some object, and all of a sudden, instantaneously, the object becomes 1,000 times larger than it was 1 moment ago. So if you all of a sudden become 1,000 times larger than you were a moment ago, what would happen? We'd all be dead in here, right? You'd just whoosh, you'd squish us out of the way, the tables get thrown, the walls would get knocked down, the ceiling would fly out. That's what happened here. There was a truck, a Ryder pickup truck, or a moving truck right here, filled to the gills with ammonium nitrate and fuel oil. The only reason the fuel oil was in there was to make the reaction happen faster. So this thing was sitting right here, and when it was allowed to decompose that solid, so you've got a big old 24-foot Ryder truck. That truck is now 1,000 to 5,000 times bigger than it was 1 moment ago. So what stopped the gas from expanding? Nothing, right? It just expanded. There's nothing left of the truck, right? The truck is just basically disintegrated. They found the axle, and that was about it. It moved the entire building out of the way, right? All of this concrete and rebar just was moved. There's a name for this. It's called an explosion. The definition of an explosion is the rapid expansion of a gas. Most people think about fire with explosion. Fire doesn't kill people in an explosion. What kills people in an explosion? How's the force kill you? What? Couple of different ways.
It's either barotrauma, which is the primary
So
injury.
explain what barotrauma is.
Last injury. That means there's all the gas in your body rapidly changes the pressure, so it destroys your lungs. I mean, anything that's got fluid in it, or, I'm sorry, gas in it, changes pressure.
Here's the other way. Blast wave comes, right? Hits the head. And then what's the brain do? Gets slammed into it. Think about you inside of so you're inside of a back of a pickup truck and somebody slams on the brakes. What do? Go forward. You're in a pickup truck and it's standing still and somebody jams the gas, right? That's what happened here. The brain is just sitting still and all of a sudden the thing inside moves. It doesn't have enough time to keep up with it. It didn't happen slowly, it happened rapidly. So the brain slams into the side of the skull. That's what kills people, not fire. If there's any burning, it's superficial at best. But they don't die from burning. They die because of blunt trauma. They were hit with something. What are they hit with in an explosion? A gas, a rapidly moving gas. So this Ryder truck, that's an explosion. How about a gun? How is a gun an explosion? No, not the bullet.
Detonation of powder.
You detonate a solid behind a projectile. And what happens to the projectile? It's propelled because behind it, they got something small and it gets 1,000 times bigger. So you have something like the size of a dime, and all of a sudden that dime is 1,000 times bigger than it was a moment ago. So it moves the thing in front of it out of the way, and the thing in front of it is a piece of lead or steel or whatever the bullet is, and it moves down the tube. Same thing, what about a grenade? How does a grenade usually kill a person? So I have a tiny little solid thing here, right? And inside of it is solid, and then that solid stuff does what? it's turned into a gas. The grenade itself is made out of metal, but it's not strong enough to withstand that gas pressure. So the gas pressure explodes. It's sort of like what would happen if you took an aerosol can, a can of hairspray, and you threw it into the fire. The gas gets, I mean, there's a liquid in here that eventually turns into a gas, and then the can can't handle it. Well, now I've got a solid instead of a liquid or gas inside, and that thing is allowed to get bigger. So grenade this big, now grenade, 15-foot radius, and all the little pieces of metal go flying out. So it's a rapid expansion of a gas. That's all we're talking about, and that's all this reaction is. So this reaction is really common. I mean, it's not an uncommon thing. It's pretty easy to do. We're actually very, very good at doing this, making things that are non-metals turn back into their gaseous state. So I go from an ionic compound into these elements that are in their elemental form. Okay.
Just out of curiosity, so this is just ammonium nitrate, right?
Yep.
Where does the fuel oil come in?
This ammonium nitrate reaction, if he had that Ryder truck and it just sat there for 200 years, it would be no ammonium nitrate left. It would all be oxygen, nitrogen, and hydrogen. But he didn't want it to wait 200 years because then there'd be no explosion. He wanted it to happen now. This just accelerates this reaction. So you do see a burst of flame and whatnot with this, but this isn't a combustion. So where does the flame come from? Well, I've got oxygen and hydrogen being created, right? So a second reaction happens almost immediately after the first reaction happens. So you evolve these gases, and then the gases just happen to be explosive on their own right, combustible on their own right. So then you get a flame. So I get big, and then they also explode on you, or they also combust on you. So you will see flame in almost all of them, even though that's not really the thing that's hurting you. Unless it's a bomb specifically designed to do that. Okay. I mean, that's all a concussion grenade is, right? A concussion grenade is composed of gases that will expand and then won't do what? They won't combust after they go. So you would throw a concussion grenade into some place that you didn't want the building, the interior of whatever it is that you're throwing in there to ignite, right? You can throw a concussion grenade like into a living room. You don't want the house to catch on fire. You just want to like knock the guy in it out or stun him so you can go in and take control. But you don't want to burn the house down. So throw in a concussion grenade instead of a regular grenade. The solid won't produce hydrogen gas. And it also isn't it doesn't shoot shrapnel all over the place. Does that make sense? The thing, when the thing that's containing it flies apart, that doesn't kill you. So they'll make it out of plastics or even cardboards, different kinds of paper. Okay, let's go and do this next one. So how many grams of...
What's that compound?
What's this one right here?
Yeah.
Anybody? Say again? No, can't say di. There's a metal there, right? It's an ionic compound. So it's manganese oxide, right? Is that enough information? So it's manganese... 7. I've got 7 oxygens, and each one of those oxygens charge is what? -2. So I've got 14 negative charges, and then I've got 2 manganeses to balance out that 14 negative. So each one of those 2 manganese have to have a charge of +7. So I've got +7 and +7, and -2 7 times, so they cancel out. So this is manganese 7 oxide. And the first one? Potassium permanganate. And then the next one? Sulfuric acid? Okay. This doesn't look balanced to me. I think we need a 2 here. And if I have a 2 there, then I've got 2 potassiums. The sulfate's maintained. I've got a, is that it? 8, 12, 4, 7, 8. Oh yeah, that worked out. Well, that was easy. States. You okay with that one being aqueous? So since that's aqueous, that one's aqueous, right? Because there's water present. The water's in the sulfuric acid. And so there's water over here. So that makes this potassium 1 aqueous. And how about this manganese 7 oxide? Solid. Because you don't have a manganese rule, but you do have an oxide rule, and the oxide rule is insoluble. So that one on that manganese 7 oxide is just rusted manganese. All right, so how many grams of this manganese 7 oxide can be formed? We've got 196 grams of the potassium permanganate. Okay, so this is asking a specific question, and in this question you have to assume what? Yeah, say it. That you have as much as the other stuff as you need. So what this one is saying is I've got 196 grams of potassium permanganate and as much sulfuric acid as I need. That's how this question has to be answered. You cannot consult the sulfuric acid because you weren't consulted in it. And so you have to assume that you've got enough to use all 196 grams of the potassium permanganate. Okay, so I've got 196 grams of KMNO4, and then 1 mole KMNO4, and then somebody got a mass on that? That sounds good. And then for every 2 moles, my KMNO4, what are we looking for? No, that's wrong. That's a 1 right there. And then I've got 2 KMNO4. Oh no, what am I doing? Two. 1. How about a mass for the manganese 7? Start flipping through homeworks.
Uh,
221.87. That sounding like about right? Yeah, that sounds good. 221.87 grams Mn2O7. Looks like 130. 137.587, something like that. Are we good with that? Why not? The 6 figures are okay, right? We need to have 6, right? And we've got 6. Okay. So now we want to know about how many grams of the potassium sulfate we can make from 390 grams of the potassium permanganate. So I've got 390 grams KMNO4. 1 mole KMnO4 and 158.0339 grams KMnO4. So far this is written out exactly as the last one, right? I haven't changed anything except my starting mass is different. And this time I'm going to be looking for 1 mole K2SO4. And for every 1 mole of K2SO4, what do we got here? 174.2602 grams K2SO4. So grams K2SO4 and how about 215.021? Oh, that's good. We all good with that? Okay. If you react 375 grams of zinc metal with 225 grams of fluorine gas, what will be left in the container once the reaction is complete? Okay. So I've got myself some zinc metal, and I've got myself some fluorine gas, and then I'm going to make myself some zinc fluoride. And the balancing is easy since it's balanced already. And everybody put F2, correct? Instead of F. So it looks like I've got 375 grams of this, and I've got 225 grams of that. All right, so let's figure this out. So 375 grams of zinc. And then for every 1 mole of zinc, 65.39 grams of zinc. And for every 1 mole zinc, 1 mole OZnF2. Every 1 mole ZnF2. Looks like about 103.3768 grams of ZnF2. $593. Okay. So now we need to do the other one. 225 grams of fluorine. Grams. For every 1 mole. F2. So okay, so not everybody did F2. You don't think this mass is right for ZnF2?
No, I was just gonna be doing that,
What'd you get?
I got 100.3768, but
103.3768.
yeah.
But 593 for the mass then?
I'm 575, but I don't know my math
Hmm. 218, is that what you said? No. All right. Yeah, so 375 divided by 65.39 times 103.3768.
Correct.
593. You good with that? And then, what do we got here? 18.998 times 2 equals, so here I've got 37.996 grams of fluorine. And for every 1 mole of fluorine, 1 mole of ZnF2. And then for 103.3768 grams of ZnF2, 1 mole ZnF2. And so 225 divided by that's times 103.3768. 612 grams. Okay, so we're trying to answer what's left in the container. So can you tell me 2 of the 3 things? Zero grams of zinc. We all right with that? The zinc ran out first. What happens when I've made 593 grams of zinc fluoride? I have no more zinc, right? I've just used it all up. But it looks like you would want to be, you could make 612 grams if you had enough zinc because of my fluorine, but I don't have that much. So I know I've got 593 grams of zinc fluoride. So an easy way to figure out the rest of this is 375 and 225 gives me 600. So I started with 600 grams. So 600 starting material, 593 end product gives me 7 grams of fluorine gas left over. So that's in the container and that's in the container. If I had more than just these 3 substances, I could just do another railroad track and calculate out the fluorine that would be needed for 375 grams of zinc, and then done the subtraction from 225, and it would have told me that it was 218 is what I needed, since I know that there's going to be 7 grams left over. Why might this be a good way to do this? Why would having leftover fluorine be a good idea if I wanted zinc fluoride? So it's obviously bad to have the fluorine gas floating around, but if I'm doing this in a hood and it's all safe and everything and I'm not worried about ingesting it or breathing it in, why would this make it easier for the person who's making zinc fluoride?
Because the product's pure, you don't have to zinc.
Well, I have fluorine, so it's not pure, but okay, so I could open the container up to the atmosphere and what would happen? The fluorine gas would just leave, and what would be left in the container? Just my zinc fluoride, right? If I did it the other way around and let the fluorine run out first, then I'd have zinc fluoride salt in there mixed in with what? Zinc solid. So then I'd have to figure out a way to separate the 2 of those guys out, which probably wouldn't be very hard. Why? So, just because it's a salt, does that mean I can dissolve it? It has to be what kind of salt? A soluble salt. Is this a soluble salt? Anybody? Maybe. Do you guys know? Are you supposed to know? It's not on the list, right? We have no zinc rule, we have no fluorine rule, but we do have what rule? We have a halogen rule, right? Kinda. We have a bromine, iodine, chlorine rule, right? And those guys are all soluble. So what's your inclination? That it's soluble. It's probably soluble. It is soluble, but if you were to guess, you should probably guess. Yeah, this follows the trend of the other halogens. So this is a guy that's probably also soluble, but you don't know that for sure. but it would be a good guess. Any questions about that?